Another very common application of vectors is to describe both lines in 2D and 3 dimensions. So this happens because if you imagine that we know a point in space, any point, and we know a vector, which is, well, some direction, we can draw any line, right? We can define a line if we just know a point in space and any vector. Basically because, well, if I just know a vector, I would have a family of lines which are parallel. So I would have an infinite number of lines which are all parallel to this vector. But as soon as I set a point, as I define a point, I will only have only a single possibility. So let's assume that I've got a point A, which I know. I've got a line which goes through that point A, and that line is parallel to this vector B. So let's say I have another point in that line, and I call this point R. So I would have some kind of origin. So this is my frame of reference, and I'm going to define all my vectors. So I've got my vector OA, I've got my vector OR, and I've got my vector AR. So basically, if I want to define an equation for this line, notice that I can rewrite this vector, which is pointing towards any point in that line. Okay, this point R could be, it's just chosen. You can choose any point. So if I want to know this vector, it's the sum of OA plus AR. There you go. Now, AR is a vector which is parallel to B. So it's basically B times something. It should be, since it's parallel, it should simply be vector B and multiplied by some vector, which I'm gonna call it T. Vector OA I can just write as another vector. I can write as vector A. So I would have this relation, this equation here, and this is called the vector equation of the line. If you express all the components, you would have this xy, right? This is position xy of any point in this line. This would be given as A1, A2. Those are the components of this points that we know, x and y that we know, plus B1, B2 times a coefficient t. And t is basically some real number. And basically that's it. This is called the vector equation of the line. This vector B here is also called the direction vector. You can notice that just as we had here, this is going to be the vector which shows us where is our line going towards, and this will slide our line across our plane. Obviously, this is the representation for a two-dimensional case, but we might have problems in which we would have a point in 3D space, and it wouldn't change very much. If we expand this vector equation, we can actually get two equations. So plus B1 t, right? That vector equation we can break it down into two equations. So a2 plus b2t. And we call those the parametric equations. Parametric, right? Those are the vector equations, and those are the parametric equations. T is called a parameter, and for each different t, which is a real number again, we're going to have a different point in that line. Now, there's a third option. If we notice, we've got t here in both equations, so we can rearrange those. We could actually express t in terms of everything else, so we can make t our subject. So here we would have x minus a1 over b1. And from the second equation here, from y, we would get y minus a2 over b2. And then we can actually get two equations from this, right? And those would be called your, we can relate those two here, right? And then if we cross multiply, then we're going to get our minus a2, that's our Cartesian equation, equal. So we cross here b2, x minus a1. That's our Cartesian. You are expected to know all those three forms, and sometimes you might be asked to take from one to another or try to derive one from some kind of problem, right? So very simply, let's say that we're given a point and we're given a direction vector. So a here, 1, 5, is a point of our line, and this vector 3, 2 is a vector which is parallel to that line. So let's say first that we want the vector equation. So simply, the vector equation, we know that's going to be xy. So it's our vector a, which, well, it's 1, 5, plus our vector, direction vector, 3, 2, and our parameter. T is a real number. That's it. This is the vector equation. Simple. Now, what if they ask us the parametric equations? Basically, we have to expand each one of the equations that we have hidden in this vector form. So we're going to have x equals 1 plus 3t, and y equals 5 plus 2t. Those are your parametric. Simple. And again, t is a real number, right? It's a member of the real set. Now the last one, we could be asked about the Cartesian equation. So for the Cartesian equation, we would express our t first, so we make t our subject. So here, if we rearrange, we're going to have x minus 1 over 3, which is also equal, if we look at the second equation here, y equals 5 plus 2t, so y minus 5 over 2. Right? Now if we cross multiply, we're going to have 2x minus 2 equal to 3y minus 15. And there we go. The only thing that we have to do here, we may rearrange a few things, right? Because we've got numbers here, so let's just express this as 2x. Let's get y on the other side, minus 3y equals negative 15 plus 2, negative 13. We could probably better to change the signs, and then there we go. Right, and there we go. So 3y minus 2x equals 13. This is also okay, right? Both would be right answers here. Now let's go for a case in 3 dimensions. So this is in 3D. We've got a point A, 1, -2, and 3, and also our direction vector. So we can now develop our vector equation and our parametric equations. So our vector equation, again, it's R is our vector, is simply vector A plus, in this case, V t, right? And this is kind of like a dot product, isn't it? Now this is a scalar, right? So let's see, R, we've got X, Y, and Z equal to, your vector A is those 3 numbers, so 1 take away 2 and 3, plus our vector, our directional vector t. And there we go. That would be our vector equation. And remember, t is a member of the real set, of the real numbers. So this is the vector. This is the vector equation. And now let's go for the parametric equations. Now again, parametric, it's very simple. You just take a look at each of those equations here individually. And so basically we split this vector into 3 different equations. So we've got x equals 1 plus 4t, y equals take away 2 plus 5t, and the last one, z equals 3 take away 6t, and t is a real number. Again, remember, we cannot forget that. One important aspect of those vectors that we have been discussing now is that, look, this is any real number, right? So what makes me choose, for example, this directional vector and not, let's say, twice those values? I could have, for example, let's say I could have x, y, z equal to y take away 2 and 3 plus, why not, 8, 10, and take away 3, I don't know, k, and k is a real number. Well, in fact, it wouldn't be a problem, but basically k and t would be related. If you can see it, right? T would have to be always 2k, so we would have the same values, right? For example, if k here is 1, this first value here would be 8, the second one 10, the third one -8. Now if k is 1, for us to get the same value, t would have to be 2. So we multiply 4 by 2 to get 8, 5 by 2 to get 10. So they're actually related. So we don't need 2 explanations for the same vector. And that's why sometimes it's very useful for us to have a unit vector here. Because then if we choose a point and then a vector which is the shortest, at least with that point we know that that's the only equation that we could get for that particular line. And then the parameter would be the same as well. Now, just as a last example, let's say that we have 2 points and we're asked, okay, what's the parametric equation for those 2 points, the parametric equations for the line which would go through those 2 points. Alright, so, well, first thing that we have to notice is that we could pick any of those 2 points as our fixed point. But well, let's just decide to keep point A. Now the second thing is, well, if I'm talking about a line which goes through point AB, and I decide to keep this point, if I want to know the vector which points from A to B, I can just, well, do AB. So it would be our directional vector. So how do we find this direction vector? Well, AB, that's the coordinates of B minus coordinates of A. So minus 1, minus 2, 0, minus 1, and 2, take away 4. So if we work this out, it would be take away 3, positive 1, and negative 2. This is our direction vector. So we could just describe x, y, z equals 2, and then we could pick either, right, of those points, either one. So I'm picking point A plus negative 3, 1, and take away 2. T is a real number. Now remember that we may have different equations here to describe this. So we could have, for example, a directional vector which goes from B to A. We would have exactly the same thing here, but with flipped signs. And then we would have a parameter which would be exactly t, but flipped sign as well. Also, this point could be B instead, and we would have something that looked different. But if we try to describe this equation, if we get each of the equations, we would arrive at the same results, just with different parameters.